We now take a look at an alternative method for finding the standard deviation, right? And it all comes back to this new way of looking at the expected value, that it doesn't just have to be the expected value of x, but it could be some function of our random variable, right? So let's kind of write down two basic results that we've developed over the last few um, videos. So first, our variance is defined as the expected value, or actually, let me go back to the summation. So our variance is the sum over all possible values of x. And remember what you do. You take each x value, you subtract the mean, you square, and then you multiply by the PDF, right? So this is our definition of our variance, and we can denote it like this, or we sometimes just use the letter V to represent the variance of our random variable. And then we came up with this idea that we can find the expected value of other functions of our random variable. So this expected value of g of x, that's another sum, and it's the sum over all possible values of x. And what we do is we take our function, evaluate it at those possible values of x, and multiply it by our PDF. Now I look at this and say to myself, I see a lot of similarities here. Right? We have two summations, right? And they're over all possible values of x, and they involve some function that's being multiplied by our PDF. So it's almost like I can think of the variance as another type of expected value. So in other words, since this is the function that is multiplying my PDF, I look at it and I say, well, this matches up with this. So in other words, I can say that my variance is actually equal to the expected value, right, of the quantity x minus mu squared, right? So in other words, if I let my g of x be equal to this quantity, and then I take the expected value of that, then that's exactly how our variance is computed. So what we can do, now that we have a few more properties of the expected value, let's rewrite this. Let's do some algebra with this and apply those properties and see if we can come up with a slightly different formula. All right. So the first thing I will do, let's expand the binomial x minus mu, right? And then I can drop the square brackets. So when I expand x minus mu squared, I will get x squared minus 2 mu x, and then plus mu squared, right? Now remember, the mean is a constant, right? It's this theoretical average. So just keep in mind, this is where mu is some real number. Now remember, we proved some linearity properties of the expected value, and we can do this. The first thing I can do, because here is a difference, here is a sum, I can break this into the expected value of three separate terms. So first I can say it's the expected value of x squared minus the expected value of 2 mu x, and then plus the expected value of mu squared. Now, because mu squared, because mu is a constant, then 2 mu is a constant, and so is mu squared. So remember what we can do with like constants that multiply our variable? We can factor them out. And also the expected value of a constant, well, since the constant never changes, its expected value is exactly mu squared, right? So again, those properties that we established previously are now pretty handy in this process. So factor out the 2 mu. So I'll have 2 mu times the expected value of x. And then the expected value of this constant is the same constant, right? And then remember that mu is just another way of writing the expected value of x. Same thing here. So what I'm going to do is wherever there's a mu, I'm going to write it as the expected value of x. I'm going to use the e notation as opposed to our Greek notation, right? So it looks like this. So I have the expected value of x squared minus 2 times the expected value of x times itself, right? And then plus the expected value of x, that quantity squared, right? Well, now I can definitely see how this simplifies, and I'll do it over 2 more lines. So we have the expected value of x squared, and then I have minus 2 times, well, e of x times e of x is e of x, that quantity squared. Well, what does this really mean? Well, the last 2 terms here, these are now like terms, and I have a minus 2 times this plus a 1 times the same thing. Add those coefficients, and I'll end up with this formula. And the formula is the expected value of x squared minus the expected value of x squared, right? And remember, this is where we started by looking at our variance. So this is our alternative formula for computing the variance of a discrete random variable, right? In fact, it goes beyond just the discrete. This is a formula that will also work when we look at the continuous cases, right? So this is a really useful formula. So let me write kind of in summary, so kind of summarizing what did we just do here, right? Well, here is the definition of the variance. It's the summation over all x of the x's minus the mean squared times the PDF values. But then we used our properties of the expected value, and we derived this other formula, this expected value of x squared minus the expected value of x squared. Right now it sounds like I'm saying the same thing, but that pause. So here what you're doing is you're finding your regular mean and squaring it, but then here you're finding the expected value of x squared, and then you take this difference to get the variance. All right, well let's see how it works. Let's do an example. And again, I'll make up a simple PDF that we can work with, and just so that the algebra doesn't get really cumbersome, and we can focus on the process as opposed to the crazy numbers. So let's say here is our PDF. Feeling like we should just use some even numbers today. So here are the possible values of x, and here are the associated probabilities. So let's say 1/2, 1/4, 1/4, right? So here's our PDF. And I think it's probably helpful to see both of these in play. In other words, let's use both approaches so we can see, again, as a reminder, because we've done this one previously. let's compute the variance using this approach, and then use our new approach and see if we end up with the same result. We better, right? Our algebra and our proof says that we should. All right, so by the first, what I'll do is let's just put a little asterisk for this one and then a double asterisk for this one. So using our approach based on the definition, let's set up our, well, first we need to find mu, right? Notice regardless of which method we're using, we have to find the expected value, right? So mu, or the expected value, that is simply the product of each x and its corresponding probability, and then you take the sum of those products. So it's 2 times 1/2 plus 4 times 1/4 plus 6 times 1/4. So what do we have there? We have 1 plus 1 plus 3/2. So that's 3.5, or I'll just write it as 7/2, right? So that's our expected value. Now let's set up that table where we, first compute the deviations, and then we square them, multiply them by the probabilities, add them all together, right? So let's do that. So again, we'll set this up as a table, so we'll illustrate the different steps as columns. So these are our x values. Now let's take each x and subtract the mean, which is 7/2. So if I take 2 minus 7/2, I'm going to get negative 3/2. If I take 4 minus 7/2, I'm going to end up with 1/2. And then if I take 6 minus 7/2, I'm going to end up with 5/2. Right? So these are the deviations from the mean. Right? And this probability distribution, it looks a little, it doesn't look symmetric, right? Because we have one value that's less than the mean, and then we have these other two that are greater than, right? Now let's square those deviations. So let's compute that. And then this is 9/4, 1/4, and then 25/4, right? And then finally now let's take the squared deviations and then multiply them by the corresponding probability. So we're going to take 9/4 times 1/2, so that's 9/8, and then 1/4 times 1/4, so that's 1/16. Right, so 1/16. And then finally 25/4 times 1/4, so that's 25/16. And then let's sum these up. So if we sum them up, okay, so let's see. We probably, so let's get a common denominator of 16. So the sum there is 18/16 plus 1/16 plus 25/16, and that's 44/16, and then that's 11/4, right? So that's the variance based on our definition, right? So let's write that down. So therefore, the variance of this random variable is 11/4. And if we wanted to be complete, we could say, and the standard deviation is the square root of this. And the square root of 11/4 is root 11/2. All right? Okay, so now let's see what it looks like if we use the alternative formula, right? And again, just so that we have all the information, let me restate our probability distribution. So we got 2, 4, 6. Here are the probability values: 1/2, 1/4, 1/4. Now we're going to use the double star approach. So our new approach is this. And it's, again, let me write the formula down. The variance of the random variable is the expected value of the square of the random variable minus the square of the expected value, right? And remember, we already found the expected value. That was our 7/2. So we have this part. What's left for us to find is this part, right? Now this is what we previously covered, that when we're finding the expected value of some other function, we simply evaluate that function at all the possible values of x, and again multiply by the corresponding probabilities and take a sum. So let's compute the expected value of x squared. Right? So we take each x and now evaluate it at this function, so it's going to be 2 squared, and then we multiply it by the corresponding probability. And then 4 squared times the corresponding probability, and finally 6 squared times the corresponding probability. So what do we have here? We have, that's 4 times 1/2, so that's 2. We have 16 times 1/4, so that's 4. And then we have 36 over 4, so that's 9. Right, so the expected value of x squared in this case is 15. Right? So now all we have to do, we know that this is 7/2. We just computed this to be 15. So our variance, so the variance is going to be 15 minus our mu, which is 7/2 squared. So what do we end up with? So this is going to be 15 minus 49 over 4. Well, that means we need to get a common denominator of 4. So this is 60 over 4 minus 49 over 4. And that gives us 11 over 4. And that's exactly what we got right here. Right? In fact, let me circle this one as well. Right? So it's an alternative approach. I don't necessarily think one is better than the other. It's a variation. But in some sense, it almost seems like this is a little faster, right? You know, we don't have to go through and do the deviations and square the deviations and then do the weighting. Either way, we have to compute the mean, right? So that's neither here nor there. It's the comparison now is completing the table with the square deviations versus computing this expected value. I think if you look purely on the number of arithmetic operations that we have to perform, then this method appears to be more efficient, right? So there's our formula, and you know, you have a choice now as far as computing the variance, what method to use, right? And I'm sure we'll make use of both methods in the future. See you then.